that runs out first. Classified metal, non-metal, we did pretty good here as well. Little trouble with the silicone as the metalloid. There was no other non-metal listed as a choice. That was not a choice. And as a matter of fact, I stood right here a couple of times and did the little doot, 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 and I said it will either be silicone, arsenic, or astatine, or something like that. Yeah.
What threw me on silicone is on my periodic table, it says it's other non-metals, so.
Right, but that's not one of the choices.
Yeah.
Okay. And in lecture, several times,
Yeah.
I said it's a metalloid. Because it's on that border, on that doot, 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 doot. All right. But other than that, pretty good. And the temperature, yeah, so most people did okay on that. You had to recognize which one of the, you have to recognize that when you're given the temperature in Fahrenheit, you're converting it, that's when you get the temperature in Celsius. So you don't plug that, that's how you use the formulas. It's not, you don't plug it into the F, how to get the Fahrenheit formula, you plug it in how to get the centigrade formula. Anyway, so that was that one. Best ever on the proton, neutron, electron charts. Tore that thing up, right, for the most part. Right, so the number next to hafnium is the mass, which is the number of protons plus the number of neutrons. The 4+ next to hafnium is the charge on hafnium, which means there are 4 more protons than there are electrons. Right. I'm going to say this. If you got under 75, you can resubmit the entire test for regrading and get half those points back. If you got over 75, no. And you may think that's not, but it is. It's completely, it's fine. Okay, all the way up to 80. All the way up to 80. So that'd be 10, that'd be 90. No, you can't have that. It's got to be 75, because that's 70 would really be. So did I say 70 the first time?
75.
That's a weird number. So you could be 12.
75.
12 would be 87. I can do that. So if you want to get up to 87, let's say it this way. You can redo your entire test if you want to get up to 87. The entire thing. Like the whole thing. Not just part of it, not just the parts you missed, the whole thing. Showing your work. Right? Do we understand? So for those of you that are going to get 7 points for doing it, you may not want to. But if you're going to get 30 points for doing it, you probably want to. Does that make sense? Or you guys understand what I'm saying? Mm-hmm. So I'm not going to write it down anywhere. It's just going to be on Maria's video or not. I don't know.
So it's under 75?
Yes.
Or 75 and under?
Yes.
Okay.
Yeah, if you got a 75, you're still in. As a matter of fact, if you got an 86, you can still do it, but you're only going to get 1 point for redoing the entire test, which is a good study tool.
Yeah, points is good work.
Yeah, exactly. All right. So next, so again, I'm very impressed with filling out that chart. It's the best I've ever seen. Give the chemical formula for aluminum permanganate. We did pretty well on this too, right? Most of us recognize that aluminum's a 3+, permanganate's a 1- because we had that on our charts that we were able to use, which I don't even allow in 120. I don't know. Give the proper name for platinum acetate. The platinum 4 acetate. Remember that was where if you got platinum 4 acetate, you got 8. If you got platinum acetate, I was kind of generous, gave you 6 because we're new. But it probably should have been 4. If you didn't get, anyway, if you got less than that, there's something going on. Then the alexophyllin drug treatment. Mostly we did very well in this as well, right? I color coordinated the numbers that went together, and as long as you use them all, you got the points. predict the formula of ionic compound by iron 3 and phosphate ion, so that'd be FePO4. Calculate the grams of 27,000 glucose molecules. And again, those of you that remembered to go from molecules to moles to grams got full credit, and maybe I missed a couple and you got credit when you shouldn't have, but that's all right. Grams, C6H12O6, right? And then times 1 mole C6H12O6, and this is where we use Avogadro's number. Oh, wait. Oops. See, I did it. See how easy it is? I was copying off the paper. 27. Oh my goodness. 27,000 glucose. Okay. C6H12O6 molecules. Oh, there we go. All right. 27,000 molecules of this, 1 mole, Avogadro's number. And then times the mass, which was, what was the mass? What was the mass? It's like 72, 84, and 64, 100 and something.
It's 180.162.
Oh yeah, 180. I should always remember that, right?
Like 80. Price of soda nowadays.
Alright, so that's that. And again, we did, like, overall, very well done on this problem as well. Balancing equations, this was, people didn't like this.
I skipped it at the beginning and I had to come back to it. I don't
They
know
were
why
hard.
it tripped me up, yeah.
Yeah, it's the combustion one is especially difficult. Those of you that had the 120 class, you might recognize that problem, and then and because it was so hard to do, and it took us hours, probably remembered it. And so our numbers should be 4. So we're looking at lead oxide, nitric acid, and with a 4 in front of it, and then lead oxide with a 3 in front of it and 2 waters. And the other one is something, what was it? 25 oxygens, 20 carbons, and what, 18?
And I think these were more difficult than my Chem 120 final.
Well, it should be.
Yeah,
This is freshman chemistry, not.
I was not prepared.
Number 11. This was one of the harder problems on purpose, right? But it was a direct copy with just a different title of what we did on the practice test. And I got to tell you, this test was a lot like the practice test, very much so. So if you're looking for ways to improve your score, do the practice test. And if you can't do the problems on the practice test, come to office hour, arrange a Zoom, talk to the people who are getting over 100 on the tests, even if they don't want to talk to you.
That happens.
You have to kind of, sometimes you just gotta build a bridge.
Bribe's going on there.
I'm completely bribable. And, okay, so this one, so we started, let's put it up there just for fun. So we had 32 cubic inches, right? And whenever we see cubic inches, I wrote cubic instead of inches. I'm way too relaxed today. 37 cubic inches. Whenever you see anything cubed, it's a volume, right? It means it has 3 dimensions. There is a number that gives us the cube change, cube to centimeters, and we want centimeters, but we want 3 directions of centimeters. So 2.54 centimeters is 1 inch, but you see that's cube, so we have to cube this, which all that means is length times width times height. And a lot of us know that that's a volume, because if you have 3 dimensions, you're defining a volume. If you have 2 dimensions, you're defining an area. And if you're having 1 dimension, you're describing a length. So length, area, volume. Okay? And so now we're in cubic centimeters, which is what we wanted to be in. I left out the step of going to milliliters. What else do we need? Oh, we need the mass in kilograms. Oh, so here we have to convert to grams somehow. And here's this, grams, 21.4. The density, 21.4 grams per centimeter cubed. And then we need kilograms. So 1 kilogram is 1,000 grams. All right. And number 12. This was harder than it should have been. The 2 numbers were 1.5662 and 1.5664. This being the high, this being the low. So this is what the plus or minus is for and how we're supposed to use it, right? So in lab, when it says measure to point, let's measure to point 001, that's measured to here. We're still gonna write this number down, but we're only looking for plus or minus in this number, right? So it could either be plus or minus 5, so for this one it could be 567 or 1.565. So anything in that range when we're measuring will work, right? It's an important concept to measure. And especially if you're using a syringe on someone, right? There's a huge difference between these 2 numbers, all right? Especially when it comes to the human body, especially when it comes to a small human body, right? Bigger human bodies have bigger tolerances. Smaller human bodies, smaller tolerances. So if you're in your backyard cooking up meth and using syringes and stuff, you want to be very careful with your dosage.
Don't blow yourself up.
And yeah, or if you're making ammonium nitrate in your backyard, also be careful. All right, so the next one, write a balanced chemical equation for the reaction with zinc and iodide. Well, we just did that in lab, so I was kind of hoping that would be a no-brainer. And I wrote it on the board wrong like 500 times, but it's supposed to be this. And then normally you put, was this liquid? And then this is a solid. But you don't have to have states, I just wanted the balanced equation. And that's, no, is that?
2 iodine.
Yeah.
So you put 2.
Yeah, this was in you could write it like this too. I give you credit, I don't care. Either way. Okay, hydrogen gas reacts with FeO3 to Fe3O4, I should say, to produce iron, metal, and water. Write the balanced equation. Normally I make you figure this one out, but I gave you the equation, all you had to do was balance it. I'm not going over that, because you need to work through that if you aren't able to do that. And there are a lot. So all these little techniques have lots of videos, right? Find somebody you like listening to and go over them. If you don't have the concept, nobody's gonna do it for you. And in order to pass this class, you have to know how to do this stuff. So either get a tutor that'll hold you accountable, make you show up for an hour, come to an office hour, watch videos on your own, get together with somebody else and have a watch party. So when I did chemistry, way back in the day, I always grabbed somebody up so that I knew I had to do it. Well, I'll be there at 11, and then walk away from whatever I was doing and do it. So, I mean, you gotta hold yourself accountable, especially if what you're trying to do is get out of the rut of, I'm gonna stay here for the rest of my life. You don't have to, okay? You don't have to, but it's hard as hell. And I wouldn't be joking if there won't be setbacks or steps in the wrong direction But that's not, especially at the ages we're looking at right now, that's not a reason to stay there, okay? Just keep moving forward. Keep separating yourself from everybody else. Take responsibility for your own success. All right, that's enough of that nonsense. Well, truth, I should say. What theoretical part yield of this reaction? Oh, this was, oh, right. Oh, this. Okay, so this is the part where it got a little bit difficult. I see they turned on the heater in the middle of the day with the sun out. Thought it was just me, COVID or something. All right, so what we've got here is we've got 8.07 grams of iron oxide. And this is what, Fe3O4, right? And you notice I've always got time. Always have time to write the label down so I know what I'm doing, right? Because even if like my mind's racing way ahead and I'm solving the problem, if this label's here and it doesn't match the label at the end, I can fix it. But if it's not here, I don't even, there's no check, right? So we check. So write the balanced equation, synthesis, number of grams, and I'm looking for hydrogen. So the first thing I have to do is go grams to moles to moles, and then moles back to grams, all right? So does somebody have a number for this? 1 mole Fe3O4.
It was kilograms.
Oh,
Convert to kilograms first.
oops, you're right, thank you. In kilograms, so we're gonna go to grams first. So we're multiply by 1,000 grams, 1 kilogram. And I like to put Fe3O4. That's not necessary, but for my crazy brain, it helps. Because if I do, here's the thing. If you do the same thing over and over and over again, it becomes a habit. And that habit is a good habit, as opposed to the other one where I don't write it down and it's a bad habit, and then someday I need to write it down and I don't because it's a bad habit. All right, so there I'm there. Now I'm going to go to moles. And I still need that molar mass.
231.546.
Yeah, that sounds right. 54546. All right. And so now I'm in moles of iron. Went kilograms to grams, grams to moles, and now we're balancing. We're going to take the numbers from the chemical equation, and which is, oh, this isn't balanced. Why am I looking? I should be looking at one that's balanced. Here we go. Then I wouldn't be asking any questions, would I? No. There we go. And then we want moles of hydrogen, 4 moles H2, and what is it, 3? No, just 1, right? 1 mole Fe3O4. And then for every 1 mole H2, there's 2 moles of H. And what's interesting is some people skip this step and then they put another 2 here and then they get it wrong because it's only times 8. It should be 8 grams of this, but if you have a 2 here, it becomes 16 grams and then you get the problem wrong. 1 mole H, and you lose a couple of points, right? Which is why I write every single thing down so I can cancel it out. I know in big brains, this is all one step, right? 8 times 1 divided by 234 times 100 times 8. And you just leave out all this, right? Because it's not necessary. Well, it isn't until it is, right? until it gets to be one step too many in your head. And you just don't remember, right? Okay, so that's that problem. And then, so that was hydrogen. Ooh, this was hydrogen gas. So hydrogen gas. So I shouldn't have done that, should I? Should have stopped. Well, now I gotta, whoops. Boy. What did this should have been, oh boy. So maybe I graded it wrong. Because I just read it as hydrogen. I didn't read it as hydrogen gas. Uh-oh. So everybody got a bunch of points because most people saw it like I did, which was just hydrogen, grams of hydrogen. But it's grams of hydrogen gas, and if I said hydrogen gas, that's H2. So what is that?
2.016.
Yeah.
With 1 mole H2.
Still comes out to be 8. So if I took points off for this answer, I'll put them back on.
So that's why I asked you, and you said no.
Well, I thought it was hydrogen. I thought I wanted to know how much hydrogen, not how much hydrogen gas. So my own bad. I did that problem wrong. And, sorry about that. Okay, and then the next one is, part B is, what is a theoretical yield of iron? So thank goodness that doesn't matter what we got in the last one, because it doesn't carry forward. And now we're gonna go 1,000 grams Fe3. So this part is exactly the same. 1 kilogram Fe3O4. And then we're gonna go with 3 moles, oops, nope, not yet. This part's the same too. And again, accountability says when I'm wrong, right? You gotta admit when you're wrong. If I'm expecting you to do it, I'm gonna do it too. And it's not making a mistake that's bad, right? It's pretending like you didn't and trying to get over on someone else. All right, so 1 mole Fe3O4. Because really, let's say you built a rocket and you're gonna send up a satellite that's gonna provide free internet for the entire continent of Africa. But instead of admitting your rocket doesn't work, you just blow up the $40 million payload. I don't know. Doesn't affect space travel, but did affect millions of people and free internet. All right, so, and there were 3 of those in a row, right, with payloads that blew up. I mean, not that I was keeping track. Okay, 1 mole, what is that? 55.65? Where am I? 55.85. And that's way above my pay grade, but it still hurts me. And so 58.40 grams of Fe. So this is the theoretical yield. If you wanted to, you could just do 4.62 kilograms over 5.84 kilograms times 100, right? Because this is the actual yield, Theo, and that problem was done. I think it was 79.1%. That's what that comes out to be. Good problem. Again, these long problems, a lot of people did, as a class, we did very well on this, better than normal. So even though we had that 2-week break where everybody forgot everything, apparently it turned out okay. Then the pyridine one is exactly like the one on the practice test, except for one different element. Instead of aluminum, it was nitrogen. But it was the same kind of layout, the same kind of problem, which is kind I love, when it's just a variation. So we started off with zero, oh, goodbye. That's enough of that. Start off with, whoa. That didn't even look like any kind of anything there. 1093 grams. And it's supposed to contain only carbon, hydrogen, and nitrogen. Which means if we find out how much carbon and nitrogen there are, carbon and hydrogen there are, we're gonna see how much nitrogen is left, right? So anything that we can determine from this original amount, we're gonna subtract out. Now it turns out we're gonna do elemental analysis on this, or combustion. And when you do combustion, you're exposing things to air. And when you expose things to air, you form compounds like CO2 and H2O. And you might even make some nitrogen oxides as well, but we're not measuring those in this case. We're only using the carbon and the hydrogen. And it says that we had 0.3880 grams of CO2 and 0.0504 grams of H2O. Okay. So this doesn't mean that this amount that we collected is more than that. It means that when combined with oxygen, the part that's carbon came from this. So if the only carbon that's going to be in this CO2 came from our sample. So we're going to find out how much CO2 is in this sample, or how much carbon is in the CO2 sample. So we're going to convert to moles. And what is that? What did we say that is? It's like 3244. All right? And then we're going to say a mole ratio, 1 mole of C per 1 mole of CO2 times, and going to go to grams, we're going to go 12.01 grams carbon, 1 mole carbon. I often take the number here for moles when doing this kind of problem. And then for hydrogen, the only hydrogen is going to come from this sample and then make water from the oxygen that it gets in the combustion. So 1 mole H2O, 18, and it can be either 1801 or 1802, depending on how you do your math. And then 2 moles of H, 1 mole H2O. And what is that? 1.0078 grams H over 1 mole H. Okay? And our numbers, I believe, are 0.084059 and equals 0.00564, and that's grams of hydrogen, grams of carbon. We can convert that back to moles of carbon, which is, why do it that step before I take that number. And that's 0.02, oops, that's not right. Well, where is it? 0.00698 0.85 moles C, and then we do the same thing for hydrogen. 1 mole hydrogen, 1.0078 grams of hydrogen equals 0. What is it? 0.005593. All right. So this number and this number are 2 of the 3 components of our sample. So if we subtract them from our starting sample, right, nitrogen grams equals 0.093 grams of CHN minus 0.084059 grams of C minus 0.00564 grams of H, and that's going to yield our total nitrogen, which is 0.071628. Oops. No, that's not right. What is that number?
0.0196.
0196.
00.
Yeah, this is not right. 00.
Oh no, not 20. 2 zeros are after the 196. Yeah.
Oh, okay.
196 followed by 2 zeros.
And that's grams of nitrogen.
Yes.
All right, and then that we have to convert that to moles of nitrogen. So 0.019600 grams N times 1 mole N divided by 14.007 grams of N. Whoa.
That's right.
Yeah, but my mole number's not right.
What's your mole number?
I don't have it.
That'll be it.
Whatever this is.
That's 0.0013993.
All right. So these are our components for the unknown sample. We have this many moles of nitrogen, this many moles of hydrogen, and this many moles of carbon. Now to find the whole number ratio, you divide the smallest number into each one. And in that case, it would be nitrogen, right? So we're going to divide 0.0139993 moles of N, and that's going to be a 1. And then we're going to do it up here, 0.0013993, and that's going to be a 2, 3,
3.99.
4. And then this one, we're going to do the same thing. And we get a, there we go. So our empirical formula, which is the smallest whole number ratio, is C5H4N. Now, we're given a molar mass in this problem that says the molar mass, so this is empirical, and the molar mass is 156.3 grams per mole. Mole minus 1, right? Get used to seeing mole minus 1. And then that means the empirical formula is this going into that. And we have, what, 72, 5 times 12, that's 60, lower. 60.1155, and then 4.28, and then 14.07. So this is 78, which is two. So the molecular formula is 2 times C5H4N or C10H8N2. So the molecular formula is the one based on the molar mass, and it's twice the empirical formula. And does that make a difference? Yes, it does, because it's not really these two units, right? They're not necessarily, it's C10H8N2. It may or may not be two of those units, but it could be connected in a different way, right? And that's called structural isomerism, and we talk about that if you get to organic. All right, the problem 15 was just naming and using your periodic table and the, so calcium carbonate, let's just do that. Most of us got everything but phosphoric acid, which is one of the ones we were supposed to memorize. Calcium carbonate, what was the next one? Magnesium hydroxide,
Yep. Phosphoric acid.
H2, phosphoric acid, which is,
H3PO4.
yeah, exactly.
Acetic
And,
acid.
right, phosphate becomes ick. 8 becomes ick. Ite becomes us. So this would be phosphorus acid, this would be phosphoric. And that holds for all the other oxyacids.
Then we have acetic acid,
Right.
and then ammonia.
So that's acetate, right, plus an acid. And some of you write it like this, and some of you write it like I do, C2H3O2. Either one is correct, but you need the H on the front.
Then ammonia.
And then ammonia is not NH4, it's NH3,
I got that one.
ammonia. Okay. And then write your own extra credit. I liked a lot of the extra credit ones were very good. And then something you were thankful for.
Something we were thankful for.
Yeah.
That's it. Very good.
The very last one in red.
Okay.
All right, so that was our test. Any questions on what we covered? Expect to see similar questions on the final, right? And again, you can, since we didn't submit these online, if you want to redo the test to get the more points, redo the entire test on separate sheets of paper. Do not take anything for granted, because I will look at them, and if you do not do the whole test, I will not give you any points at all. So, up to you. All right. And that was a lot longer than I thought.
38 minutes.
Wow, usually it doesn't take me that long to do a test of my own. I need a break, it's hot up here. I feel like I'm in the desert.
Don't believe there's a place on Canvas to resubmit the test. It pops up on grading, but I don't think you're able to submit under it.
Yeah,
What did you say?
yeah, it says online.
Are you?
It should, well, when I get there, I'll make sure that it's available. I'm pretty sure you don't have it done already.
It may just be, it may just be my
He's just
phone.
told us.
Well, no, I mean, there have been several issues with people not being able to submit, and even though it says online, I don't know what, and I don't close out assignments, so I'm not sure what's going on,
Hmm?
but,
Yeah, you think it's low? Yeah. Yes. Yeah, I think it time locked itself by the date.
yeah, but usually, maybe that's a new feature.
If
Like
it's past the,
certain
date.
7 days past the due date, it
Yeah,
locks.
something.
It could be. That sounds like something Canvas would do without asking me.
To be honest.
All right, so we started a couple of lectures, and I want to go back. I don't know if you noticed, but on Canvas I put up practice problems for the material we're covering. at any time that I'm covering that type of problem or we're talking about them, feel free to ask for me to do one of those problems, or when I say any questions, feel free to ask me to do one of those problems. Otherwise, I'm just going to stick to the lecture slides. And I do like to work those out on the board as well. Let me get, so I'm just going to start from where we are, and in lab I'm going to do a little bit of, maybe I'll go back. Well, I better get that one on here too. I better start with where we didn't finish as opposed to going forward. That's what I planned on doing. Oh, I don't have a mask on, so I gotta watch my under
Yeah.
my breath comments.
Wearing under breath.
Oopsies.
Yeah, we got used to that.
You know, making faces at people like, oh wait,
No.
no mask, ma'am, you did not see that.
Yeah. I'm sorry, officer.
My coworker the other day was like, "You just bounced from the book." There's no mask on. No. It's
I'm glad to see so many of you came back. You didn't just all disappear. It's kind of nice. I thought we'd be about half size already. No? No such luck. You guys are way smarter than me.
It's still 10.
I'm starting to be the dumbest guy in the room all the time. It's nice. No pressure.
Not as long as I'm here.
That's my comment, Dom. All right. There we go. So let's start with this and see where we are. Right, so recovering molarity, right? When we put a solution together, we want to have an idea of how much of each portion there is solute, solvent, right? Solute is what's dissolved, solvent is what you dissolve it in. Usually it's just the larger amount is the solvent and the smaller amount is the solute. And we keep track of that by what we call molarity. And when we do a molarity, we're talking about moles per liter. If you saw the nitric acid announcement, it's 16 molar concentrated, and there's another way of looking at it, which is weight percent. 70% of nitric acid out of 100 is nitric acid. So it's more than the water in it. So 70% of the weight is nitric acid, 30% of the weight is water. Okay. We're just gonna have to get used to the idea. I spilled a little bit of concentrated nitric acid. We were doing organic lab and somebody did something and I didn't have gloves on. And it just turns your fingers a little brown. I mean, I used to have pale white skin, but then I worked with nitric acid. No, that's not true.
Shower in it.
That's not true. I'm showering it every day. All right. Slideshow. All right, so we did this. We already covered this. That. I like this. This is how the weight thing goes, right? And this is a cute little story about the British merchant marine or British Marines, sailors, right? It's always some guy in management. You got a bunch of people doing just fine with the way they are, drinking a keg of rum a week or whatever. And they're like, we could make more money if we only drank half a keg a week. Anyway, so they diluted it with water. So were the British sailors actually less drunk after 1740? Apparently not, because the Americans kicked their butts. Okay, dilution does not change the amount of solute present, but it does lower the molarity, right? So the more solvents you add, the less molarity you have, right? moles of solute is a constant, V times M. So the volume and concentration times the molarity and concentration equals dilution concentrations. So what that's really telling us is, and don't worry about this part. This is the part that we need. This is the part we need. V1 M1 equals V2 M2. V1 M1 equals V2 M2.
Where does it say that?
It doesn't,
Oh.
I know, I was like,
Oh
did
my
you write
God.
but that's the deal,
So write
right?
this out.
To dilute things, if you have a concentration of one, you make a concentration of another. It doesn't say that. It says that right here, right? But in not the same language as we're used to seeing. It's just V1 M1 equals V2 M2, which is could be in the reading. I'm not sure where it went. It's supposed to be on a slide right there. It's not. So how many mils of 12 molar HCl are needed to prepare 20 liters of 0.1 molar HCl? So the hard way is you get the moles needed, right? And then you divide by the molarity. And we're not going to do that. We're going to do this, right? Which is V1 M1 equals V2 M2, right? So what you already have, your concentrated acid, V1, the molarity of that acid. So let's say 10 mils of this at 16 molar. The volume of the diluted by the molarity of the diluted. So M2, V2. Right, so right here. So if we wanted to know the volume of the concentrated, we had 20 liters times 1 mole divided by 12 molar, right? So that those numbers don't really make any sense to us. So let's just roll it out, right? And what am I saying, really? What I'm saying is I have two solutions. I have a solution that exists and a solution I want to make. Because I have this bottle of chemicals that I want to use, like nitric acid, and let's just use nitric acid. How about that? So I'm going to say V1 M1 equals V2 M2. And why is that true? Let's look at the units. The volume is in liters, and molarity is in moles per liter. The volume is in liters. The molarity is in moles per liter. Liters cancel, moles equals moles, right? So the moles are going to be the same, right? Or the liters are going to be the same, one of the two, right? So what we have here, what was our problem? 12 molar HCl. 12 molar, so 12 molar, which whenever I see the big M, I always write this way, right? So I'm going to do that. And then I want, what do I want? I want how many mLs of 12 molar HCl are needed to prepare 20 liters of 0.1 molar. So 20 liters of 0.100 molar HCl. And that's 20 liters of HCl. And I have 12.0 molar, and I want to know liters, but I'll change it to milliliters later. So right now, this is my V1, is what I want to know. I have a molarity that I want it to be, and I want to prepare this much, and so how much of the concentrated acid do I need? And so I just do 20 liters times 0.100 moles per liter, right? Liters cancel. And then now I'm going to divide all that. I'm going to move this over. 12.0 moles per liter. And now moles cancel, and I'm left in liters. So 0.2 divided by 12. Which is what, 0.24? 2.4? I don't know. What's that now? Oh, it's right here. No, it's 0.167. That's weird. 0.167 liters or 167 milliliters. Yeah? You guys see that? So if I start with an acid and I know the molarity and the volume, and I know the molarity of what I want to make, it's pretty easy to tell the volume I'm going to make. That probably would have been a little bit more helpful. But molarity is not the only way we measure solutions. We also do what we call mass percent, which is the mass of the solute over the mass of the solution times 100. Common in the commercial world, where all you want to do is how much solution do you have to weigh out to get a weight of the active ingredient, often abbreviated as W over W percent. And that's where I was talking about in the ad, the announcement about nitric acid, it being 70% WW. So volume percent is the volume of the solvent, solute over the volume of the solution. It's also common in alcoholic beverages, often abbreviated as volume over volume percent. So we're always looking at the ratio between what's dissolved in how much solution. That's the key, and it's an easy concept. So a stock solution of sodium hydroxide, 40 grams per mole, is labeled as 20.5% by mass and has a density of 1.016 grams per mole. What is the molarity of the solution? And then base the calculation on 1 liter of solution. So we need grams of NaOH in this 1 liter solution. So we're going to take 1 liter of sodium hydroxide, which we're going to convert to milliliters, and then we're going to multiply it by the density in grams per milliliter, right? So 1,000 milliliters times grams per milliliter is going to give us grams, right? So we have a flask with 1,000 milliliters of solution in it, and we have a density that tells us in 1,000 milliliters we have a certain mass, right, per milliliter, 1.016 grams per milliliter. So that's 1,016 grams, right? Because 1.016 grams of sodium hydroxide times 1,000 is 1,016. So now we need the part of that that is sodium hydroxide. And we know what? That 20% of the solution is sodium hydroxide. So we're going to measure that, multiply that by 0.205 grams sodium hydroxide per 1 gram of sodium hydroxide solution. Does that make sense?
Mm-hmm.
Right. So out of 100 grams, 20.5 grams would be sodium hydroxide. So out of 1 gram, 0.205 grams would be sodium hydroxide. So we multiply that times the total mass of our solution, right? And 235.9 grams of 1,000 grams is sodium hydroxide. And so we're getting closer, right? So now we're gonna say 235.9 grams of sodium hydroxide, I left the grams out, times mole, bad boy, times 1 mole sodium hydroxide divided by 40.0 grams of sodium hydroxide, right? So we take the amount that's in 1,000 grams, which is what? 1 liter, and we convert that to moles, and now we're in moles per liter, right? And that comes out to be 5.9 molar sodium hydroxide. Right. So when I was in Laramie, cowboy, that's what they called it, Wyoming guys, cowboys. And there were real cowboys there too. People at the university are cowboys. Anyway, a pale ale is offered at the Tap House, which is one of the little places there. And, you know, Laramie's about the size of San Luis Obispo. But it's in the middle of the Rocky Mountains, about 7,000 feet. Wind blows at like 70 miles an hour. Florida, they call that a hurricane. Wyoming, it's just another day. All right, so anyway, pale ale, one of my favorite beers, listed as having a 5.7 volume percent with a specific gravity of 1.102. How many grams of ethanol are in a pint of beer? Ethanol is 46.06 grams per mole with a density of 0.789 grams per milliliter. Actually, we only need the solution volume, the VV, and ethanol's density, the molar mass, and the specific gravity values are superfluous, right? Means extra, don't need it. Not really, doesn't really matter. Just to be thorough and confusing.
Confusing.
Beware of extra data that you don't need. Because life is filled with extra data you don't need.
Yeah.
Right? Yeah. So we're going to start with 480 mils of pale ale. That part we do need, right? Because that's how much is in a pint. And then we're going to say 5.7% volume over volume. So out of every 100 milliliters, 5.7 milliliters are ethanol. Okay. So milliliters cancel. Of pale ale cancel, I should say. And then the density of ethanol is 0.789 grams of ethanol per 1 milliliter of ethanol. So we get a total of 21.6 grams of ethanol per pint of pale ale.
It's good to know.
Yeah, like you could do that for anything.
So is that pretty equivalent to, cause there's this like alcoholic drink you can buy, it's about this big and it's 20% alcohol, and then if you buy a big bottle, it's 20% alcohol, would those be different?
No,
So it's still the same, it's just,
yeah, because it's a percent volume. It's just less alcohol because it's a smaller volume.
okay.
But the ratio of how much you drink of it is going to be the same. So, and we're used to seeing volume. So, a volume of 5.7 out of 100 would be it's twice that would be the proof, right? So this would be 11.4 proof, but 5.7% alcohol. And like, so all your pub brews, they're always talking this number. This much alcohol per 100 milliliters. So when you see a beer that's 11% alcohol, it just means it's 11 milliliters out of the 100.
Got it.
Yeah.
Very interesting.
But it makes a difference, right? 3% alcohol like in Coors compared to pub beer makes a difference. Whether you throw up in the Uber or not. Because nobody's dumb enough to drive anymore. It's like the best thing that could have ever happened on the planet is generation being raised to go, oh, no, I'm not driving, no matter what. And turning getting there and going back into a fun part of the experience. All right, so one last thing is mass percent, and that's going to be the mass of the solute by the mass of the solution. Okay, common in the commercial world, again, where all you want to know is how much solution do you have to weigh out to get the weight, and it's W over W. Wait, this is the same, that's the same, we already did that. Okay, so we already talked about those. That's a superfluous slide. You see how I came back to that?
All back.
Yeah, we already went over this one, so you already have this information. Like I even know what I'm doing. Okay, so we're back to stoichiometry again, which we all know now is the coefficient in front of the balanced chemical equation. It's the ratio of moles of reactants to each other and the moles of reactants to the products and the ratio of the products together. So chemical reactions involve rearrangement of atoms. No atoms are created or destroyed. Old Dalton did that. Not James Bond, Timothy Dalton, but Dalton, the chemist. And we've done the balanced chemical reactions where A is the number in front of, little a is the number in front of big A, the coefficient, right? And the balanced coefficients can go all the way through. So we have reactants on the left, products on the right, and stoichiometric coefficients are the prefixes in front, the A, B, C, D, etc. And get used. Like that's one of the things that makes all science and math difficult is we're showing you the average way of looking at something with letters instead of the numbers. Like, because if this was 1, 2, 3, you'd be like, okay, the coefficient. But instead, it's ABC, and so we see it a little bit differently, right? But it's one of those obscurity type things. So how do we translate that into chemical reactions? Titanium 4 chloride and water react to form titanium 4 oxide and hydrochloric acid. So we separate into reactants and products from our nomenclature, TiCl4. Remember, this 4 is the charge on the metal atom, and we know it's a transition metal because it has a Roman numeral, and chloride is a -1 because it's a halogen. So we're gonna have 4 chlorides per 1 titanium, and then water, H2O, and then TiO4 because oxygen is a -2, and so is the element below it. And so 2 -2s is a -4. It's titanium 4 oxide, so 1 titanium at +4, 2 oxygens at 2- gives us titanium oxide, and then HCl. We've got a couple more minutes. Arrange into an equation. TiCl4, the reactant, plus water yields, the arrow, we always say yields, TiO2 plus HCl. Indicate the physical states. Liquid, solid, gas. And remember, when we're looking at water as a reactant or formed product, it gets an L, right? If it's just in the equation, it gets an AQ. Right? And then forms HCl or HCl aqueous. So those are our states. And again, you may not be right on the states. I'm not as concerned with the states as I am with getting the element in the reactant spot with the right nomenclature or formula. Balance the equation by adjusting the coefficients. Start with the elements that appear only once on each side. It's the easiest. I chase the metals. That's what I do. Balance free elements last. Balance unchanged groups of atoms together as units. This is the key because it will work if you separate all the elements, but why make extra work for yourself? It's already confusing. Never change subscripts, only coefficients. That's the key, right? Once a compound is put together, you can't change its relationship to the other element. You can only add it as a compound. Choose the smallest possible integral coefficients whenever possible, not integrals, right? 1, 2, 3, 4. So if this was 2, 2, 2, 2, we'd be able to divide all those by 2 and get 1, 1, 1, 1. Right? So if you have a multiple of it, we want to always go to the smallest amount. Practice. N2 plus H2 equals NH3. So I look at that and I say 1 N2, 2 H2, 3 H2, and then 2 NH3. Right? 1 N2, 3 H2, 2NH3. And hexane, C6H14. Okay, so whenever you see combustion, you throw in an O2. Whenever you see a hydrocarbon, a compound containing hydrogen and carbon, you know you make CO2 in the water. That's the big deal. So the big deal that we have is we want to be carbon neutral, they say. So we don't want to burn excess carbon dioxide, and that's what we're turning these chain hydrocarbons into carbon dioxide and water, and apparently carbon dioxide is bad, and we can't absorb it because we don't have as many trees. Plants absorb CO2, do respiration, we all know that, and they produce oxygen, so if you don't have as many plants, you can't make as much oxygen, and the world gets CO2 deficient, oxygen deficient and CO2 overcharged. So what does that have to say? Let's start with a 6. I like to start with a 6 because we've got 6 carbons, right? So put a 6 here, and then 14, so 7 there. Well, that's not going to work, right? We're going to have 2. So I'm going to put 12 here and a 14 there. And then what's that? How many O's do we have to have then? 12 and 14 is 26. And so 13 O2s. So 2 C6H14, 13 O2, 12 CO2, and 14 H2. Oh, one more? Okay, we're not doing this. That's too many. Because it's time to go. So we didn't get very far today, but we will pick up where we left off. And let's take 10 minutes or so to decompress from the amazing test scores. Remember, if you got under 60, you probably should be getting help. Actually, if you got under 70, you should probably be getting help. And if you feel like I was overly generous with points, you should probably be getting help. But I'm not overly generous with points.